I'm honored to be part of this workshop with so many excellent researchers in haptics. So today I want to talk about a possible approach moving from a human haptic perception modeling to the design of haptic interfaces. So as an haptician, I have been encountered many challenges in haptic interface design. So basically, this is the haptician, and the goal is try to reach the capabilities of human touch. So it's very, very challenging. And the objective is to design a haptic interfaces. Of course, many of you know what a haptic interface is, but basically is a mechatronic device which is equipped with sensors and actuators and control mechanisms to sense touch-related information and then to convey it to the user for many different applications. For example, virtual, and augmented reality, prosthetics, or telerobotics. And there are two main types of haptic interfaces: grounded, where the base is fixed, and wearable. These systems can be worn by the users, and these could help to increase the naturalness and also the stability for telerobotics of the interaction. And of course, I'm going to discuss the latter type of interfaces. And when we are going to design a haptic system, a haptic interface, the two key ingredients for a successful haptic interface are modality matching and somatotopic matching. So basically, this means that if I want to reproduce through a haptic system, for example, the sensation of pressing with the thumb against an object, I should convey pressure information at the thumb, so I can respect and fulfill both the requirements. So both the modality, pressure, and the location. This is an example. For example, if I want to mimic a hand of a person that is pressing the arm of a user, I could try to reproduce the normal and the tangential stimulation at the arm level, where the stimulation should naturally occur. But of course, try to reach the modality matching and to satisfy the modality matching paradigm is not easy, because human touch is a very complex system. The mechanics of touch is very complex. After an interaction with an object, we can observe a complex state of strain and a complex system of receptors. So it's very hard to measure this strain distribution, and even harder to actuate. And of course, we cannot try to merely mimic this type of distribution. But what we can do is to take inspiration from neuroscience, but as engineers, what we can try to reach with this inspiration is to get a baseline and then a mathematical model of the neuroscientific observations that can be used to translate this observation into a language that can be implemented in an artificial system. And of course, this system, in particular a haptic interface, should interact with humans. So it is important to validate the system with experiment with human subjects. Regarding somatotopic matching, of course, this is the example. The real stimulus and the stimulus, for example, in VR, AR should be experienced at the same location. This is not easy, especially in tactile augmented reality. Here you can see an example of tactile augmented reality. Here you have the natural stimulus application point, but the stimulus is applied by the device in a different point to allow the finger pad of the user to experience the object that he or she is touching. So a possible solution is to use fabrics as interaction surface, because of course the fabrics allow to superimpose tactile effects on real objects without impairing the sensation at the finger pad. And this is an example that I will show you later. Here, the device stimulus application point and the natural stimulus application point are at the same location. So the user can still touch the object with their hands, but at the same time, he or she can experience additional tactile effects that we can superimpose. And at the same time, the intrinsic wearability of fabrics allow to develop artificial devices that can be easily worn and can guarantee highly natural human-machine interaction in different application areas. For example, I will show you briefly two applications. This is a system that can provide both normal and tangential cues at the arm. And some applications here, this is an application for the assistance to blind people during autonomous walking. And in the other video, there is the result of a collaboration with the Rice University and Dr. O'Malley about the usage of this system to spatially separate the haptic guidance from task dynamics during the training or rehabilitation. So the solution I want to discuss about is to combine neuroscientific inspiration and fabrics to meet these two requirements, modality and somatotopic matching. And I will start from the modality matching and the neuroscientific inspiration, and then I will discuss somatotopic matching and application to tactile augmented reality. So regarding modality matching, what I have previously discussed is that we have to try to produce some mathematical descriptors and abstractions of the complexity of human touch. And one possible hypothesis is the tactile flow. So if you imagine to interact with an object, when you press against this object, we can observe as soon as the force has increased, we can observe an expansion of isostrain surfaces within the finger pad. And we can describe this isostrain surface expansion using a model which is the tactile flow and can be described by this equation. But this equation, the constraint equation, defines the flow for each point except for those components that are tangent to the iso-intensity curve itself. So the equation is ill-posed and can produce some illusions. And one illusion that we have demonstrated in this study is to validate if tactile flow can provide also proprioceptive cue for hand motion control. In other terms, if the tactile flow model is a valid model to describe the dynamic interaction of the finger pad against the surface, we should appreciate and observe the illusion that derive directly from the constraint equation. So basically, what we did is to ask subjects to move their finger pad to reach a location and over a rigid plate. So when the finger pad moves over the ridges, because of the aperture problem that can be also observed in vision, the tactile flow provide an estimation of the direction which is perpendicular to the ridges. But at the same time, we also have the motor command, the proprioceptive estimation, which is unbiased, which tells the user that he or she is going toward the goal, which in this case is in front of the user. So the resultant estimation is a combination of these two estimates that you can see here. And the user has the perception to move in a direction which is biased according to the orientation of the ridges. And for this reason, he or she try to correct the direction in order to still reach the goal. And we have modeled this behavior using a Kalman filter approach. And our results in this video, you can see what I have previously mentioned. You can see the motor command, the perceived direction, and the correction. So the perceived direction is a combination of the motor command and the tactile flow estimate. We performed many experiments by varying the orientation of the ridges and varying also the location of the target. And what we found is that there was an angular deviation of the hand trajectory, which is function of the ridges. And this deviation is statistically significant. So we found that the orientation of the ridges produced bias in a motion direction, and the tactile feedback induced an illusory sensation of bending toward a direction which is perpendicular to the ridges. So our model, which was defined according to a constraint equation, which is ill pose, seems to work well. So this is the first part, neuroscience, mathematical modeling. The next question is how to use this model for haptic device design. So we are in this part of this diagram. So the other relationship that I want to stress is that the tactile flow is also associated to another effect, which is the contact area spread rate, which represents an integral form of the tactile flow. Basically, this concept means that when we press an object, the softer is the object, the larger is the growth of the contact area over the fingerpad. And this is basically the integral form of the previous model that we demonstrated. So we can use this relationship to build devices that can simply control the contact area based on the user force over the surface. And here you can see this grounded system, which is called FYD2. Basically, we use a fabric and we can modulate the stretching state of the fabric based on the force exerted by the user and the measured contact area. So we can mimic different softness profiles. And here you can see the performance, the reference, and the control and the control contact area that we are able to achieve with this system. The next step was to move from a grounded device toward the wearable one. And we built the wearable FYD. Basically, there are many different types of wearable systems at the fingertip level, but none of these systems can deliver both passive and active softness information and tangential cues. So basically, this is the system. In the active touch mode, the user can actively indent the fabric surface that we still used in this kind of system. And we were able to change the stretching state of this fabric by controlling two motors here. And based on the indentation that the user exerted on the surface, measured through an infrared sensor, we can modulate the stretching state. And this is a video to show what we were able to mimic with this system. At the same time, we wanted to reproduce also a passive touch system. So the finger should be fixed, so the finger cannot move. And what we did is to change the stretching state of the fabric, but at the same time, we use a lifting mechanism to put the fabric whose stretching state is modulated using the same DC motor in contact with the user fingerpad, which is still. And here you can see an animation. In this way, we were able to decouple the control of the stiffness from the pressing force. And this is what we try to replicate it. At the same time, if the two motors rotate toward the same direction, we were able to reproduce the sensation of sliding over a surface. What we did was to characterize the system for different stretching states of the fabric, so different motor position. And we found a relationship between the stiffness and the motor position theta. And we use this relationship to reproduce different stiffness profiles, linear and nonlinear, simply inverting this relationship here. And of course, in this case, we need to know the indentation, and this indentation is provided by the infrared sensors in the active touch mode and by the commanded position of the lifting mechanism in the passive one. And the performance were quite good. This is a representative trial, and we get a percentage normalized root mean square error around 80%, which is 80%, sorry, 80%, which is comparable with other work in literature. Once we developed a system, especially a haptic interface, we cannot be satisfied only based on quantitative measurement of the control mechanisms. We have to produce something to be used by humans. So we have to go back to humans. And what we have to do is to test, for example, which is the just noticeable difference. So the minimum amount of stimulus difference that can elicit a perception, a different perceptual response in the users. And we tested this GND, we computed this GND for different conditions, active touch, passive touch, but we wanted to understand if the weight of the device was a problem or not. So at the same, to do this, we used the generalized linear mixed model to compute the psychophysical curve with the method of constant stimuli. So basically, generalized linear mixed model allow to account for the effect of the experimental variables and for the variability between participants by means of fixed and random effect parameters. And in this case, we wanted to test whether the compliance of the fabric and the modality of exploration affected the perceived softness in the users. And this is the model, so the compliance, the modality of exploration, and the fixed and random effects. And these are the results. And you can see here that the confidence intervals for the GND estimation, sorry, in the four conditions were largely overlapped each other. So we can conclude that the weight of the device does not impair the user's capabilities in softness recognition, and there is no difference between active and passive exploration. Of course, another important point, user's opinion matters. So what we also did is to perform a subjective quantitative evaluation to understand if the device was well received by users. And we found that the system was evaluated as intuitive, effective, and unobtrusive. So we were quite happy about the system itself. The last part is related to somatotopic matching. So of course, as I said, if we use a fabric as interaction surface, we can superimpose tactile effects on real objects without impairing cutaneous sensations. And this is very important for tactile augmented reality. And we implemented this paradigm for surgical training. Basically, we did a work where we were asked to superimpose the effect of an artery pulse while the physicians experienced and palpated artificial organs. So the artificial organs replicated the mechanical characteristics of the human organs, but they wanted to have additional effects like an artery pulse. So to do this, we control our system to induce a sawtooth variation for the lifting mechanisms, and in order to induce the formation of the finger pad that simulates the pulsing artery. And here you can see the system, and here you can see what we try to simulate: the approximation of a pulse pressure waveform and the simulated waveform that we implemented in our system using a bang-bang control. So based on the distance between the finger pad and the artificial artery and the force that the user was exerted on the artificial artery, we control the movement of the lifting mechanisms to reproduce the pulse of the artery, of the human artery. And here, this is the control that we implemented. So basically, we try to replicate the maximum amplitude of the pressure for the artery pulse based on the measured force and the two thresholds of the force, which correspond to the standard diastolic pressure and the standard systolic pressure. And the other activation component was related to the distance of the finger with respect to the artery. And of course, we can vary, we can control the period of this sawtooth by reproducing different heart rate parameters of patients. And we tested this system. Again, the system was thought for surgeons. So we tested this system with general surgeons and vascular surgeons. They were able to still palpate the artificial artery, and at the same time they experience this effect at their finger pad. And we again use a subjective quantitative evaluation to understand if the feedback was evaluated as intuitive and effective. And we found good results. Of course, we also received some comments on how to improve it, for example, to increase its wearability, but the intuitiveness and the effectiveness of the feedback was evaluated as very good. And this pushed us to continue the investigation of this kind of wearable system for applications in gynecologic robotic surgery to reproduce the stiffness of myomas presented in the uterine tissues. And also in this case, the results were quite promising, because our system using teleoperation allow recognition of this kind of tissues with embedded myomas comparable to the one that the surgeons can achieve using their own hands. And again, another point to stress is that using a wearable system like this, we can completely rely on sensory substitution, and the control loop of a telerobotic system is intrinsically stable. So to conclude my talk, of course, there are many types of approaches to build haptic systems. What my group and I try to do is to start from the human example and try to model this example in a language that can be implemented in an artificial system. Of course, the modeling is important, but it is also important to verify after the device has been designed, the effectiveness of the system during the interaction with the users. And of course, users' opinion matters. This is one of the key, one of the most important lessons I have learned. So we can build very nice and beautiful systems, but this system must be used by people. So it is important to assess the perceptor response inducing user, but at the same time, also their subjective quantitative evaluation matters. And finally, the usage of fabrics could be a possible approach for increasing the wearability of the system and also for tactile augmented reality. This could be the key to fulfill both somatotopic and modality matching. Thank you very much for the attention.
Great. Thank you very much, Dr. Bianchi. That was absolutely fascinating. So as mentioned before, please go ahead and put in your Q&A, your questions in the Q&A panel, and we'll get to it later on during our panel. At this point, we're going to go ahead and start getting set up for our next talk. And we'll have a couple of minutes of pausing in between here. Yes.
It looks like we have one quick question for Matteo. Since we have a few minutes, do you want to take that now? So Matteo, the question is from Munya. Hi, Munya. She's curious about the characteristics of the fabric. What are the potential effects of changing the fabric type?
Yeah. So hi, Munya. Nice to see you. Yeah, of course, this is a very, very interesting question. We chose this fabric because it was a bielastic fabric. So we were able to change the stretching state along two orthogonal directions. And at the same time, this fabric allow for a good level of elasticity, and the viscoelastic effect is not so significant. So, of course, we have to take into account the different elements when we chose the fabric, and also the range that we can achieve using a particular fabric is very, very important.
Wonderful. Thank you very much. Oh, wow, we're getting even more questions. Great. With that, we're going to hold off, I think, on the other questions, just so we can make sure that Dr. Schneider has the time to practice the screen share there. Thank you, Dr. Bianchi. And
thank you, Zane.
We'll see you in a few hours.